Okay, we'll get back to section 7.5 here. So in this section, again, there's just a collection of random integrals, and the idea is for us to come up with the method for integrating. So I think we did this problem here in the last video. Now what if we want to integrate this problem here, which is x times tangent inverse of x dx. Okay, so because I got x times a function, that kind of suggests that I'd want to consider using integration by parts to begin with. In general, whenever you have x to the n times a function, you'll usually think, integration by parts to start. So here, if I let u be tangent inverse of x, dv be x dx, then du is 1 over x squared plus 1 dx, and v is 1/2 x squared dx. So I would not have those flipped. Just a second, because I'm getting my other notes from section 7.1 here. I would not have those switched, because if I were to let dv be tangent inverse of x, well, here's the antiderivative of that. So it's x times tangent inverse of x minus 1/2 times the ln of the absolute value of 1 plus x squared. So that's I'm not going to want that in my dv part. Okay. So even though I'm increasing the power by 1 here, that's fine. I'd rather have this guy than this other thing that I just read you. So u times v is 1/2 x squared times tangent inverse of x minus the integral for v to u. That's 1/2. That's a constant that can come out of the antiderivative. So then I got x squared divided by x squared plus 1 dx inside the integral. Okay. Now the next thing is that because these powers match, I'd want to use division. I guess the only other thing that I'd be thinking of is a u substitution. That's not going to work though, because if I let u be the denominator, u equals x squared plus 1, du would be 2x dx. I don't have an x dx, I get an x squared dx up top. So that's not going to work. But if I divide this out, and I've got the division shown there, so x squared plus 1, that's going to go outside the division bar, x squared is going to go underneath it. And to begin dividing, I have a 1 up top. 1 times x squared plus 1 is x squared plus 1. We're subtracting these functions. X squared minus x squared is 0. 0 minus 1 is -1. Okay? And I'll have leftover information. So, you're always adding the leftover information. The complete leftover information would be -1 divided by x squared plus 1. Okay? So I got this this line kind of rewritten here again with the division process shown. And now I want to find the antiderivative of 1 minus 1 divided by x squared plus 1. Well, the antiderivative of 1 is x, right? The antiderivative of 1 over x squared plus 1, that's tangent inverse of x. Okay, so we can go right to the answer. We're going to have 1/2 x squared tangent inverse of x from this part, minus 1/2 x, and then plus, negative times negative is positive, 1/2, bring the 1/2 there, times tangent inverse of x, plus a constant. That'd be the answer there. Okay. This next problem, so there's a couple of problems here where you're going to use a u substitution, and don't immediately rule out a u substitution. You might need some algebra within the u substitution. Okay, so there's there's nothing that I can do to simplify this integrand. If I let u be x plus 2, then du is dx, right? I got an x term out here. Well, I can know what x is from this substitution. So if I solve this equation for x, u minus 2 equals x, and so I'll replace x with u minus 2. The x plus 2 is going to be replaced with u. And du is going to be, dx is going to be replaced with du. So that's going to work. I'm going to have the antiderivative of u minus 2 times the square root of u du. And then when I distribute the square root of u into those terms there, I have u times the square root of u, that'd be u to the 3/2, minus u to the 2u to the 1/2 du. Okay, and then we can get the antiderivative of that using the reverse power rule. Add 1 to the power divided by the new power, so we got u to the 5/2 times 2/5 minus u to the 3/2 times 2/3 times 2, that'd be 4/3, so minus 4/3 u to the 3/2 plus a constant. The last thing that I want to do here is get my answer in terms of x. Right, the original integral was in terms of x, so u is x plus 2. So where I see u, I'll replace that with x plus 2. And this guy here would be my answer then. Okay, this integral is actually a Calc 1 integral. There's Calc 1 students can learn about use substitutions and that, but they also learn about a little bit of algebra going on inside the integrand, right? I don't know of any one of my other integration techniques that I'm using here. Although, if I want to, I could actually do this by using integration by parts. That makes the problem go a lot longer than what you see here, but that would be another option though that you could do. For this example, so I got the antiderivative of sine x divided by 1 plus x squared dx, and I'm going from negative pi to pi. Okay, so the idea with this function is that this is an odd function. An odd function means that if I plug in negative x for x, that'd be the same thing as throwing a negative in front of the entire function. Well, the sine function is an example of an odd function. Sine of negative x, that's the same thing as negative sine of x. And when I replace x with a negative x down here, negative x squared is the same as x squared, right? So when I replace this whole integrand with negative x, I have sine of negative x divided by 1 plus negative x squared. That's the same thing as negative sine x divided by 1 plus x squared. Okay, so that's why this is an odd function, is because f of negative x is the same thing as negative f of x. The bounds are opposites of each other. Okay, so the answer is going to be 0. Okay, and the reason why it's 0 is because the area that is to the left of 0, from 0 to pi, is going to be the same size as the area that is to the right of 0, from 0 to pi. And also the area that's to the left of 0 is going to be underneath the x-axis. Okay, so those two regions there would offset each other. Now, this integral is an impossible integral if the bounds were, other numbers. Okay, so like if I were going from negative pi over 2 to pi, that's impossible. You can't do that integral, okay? And again, that's what makes integration, more difficult than derivatives. I've said that. Because you could be doing an impossible problem. Now, again, they're not going to give you impossible problems here, but it's worth saying that some of these problems are very difficult, okay, and you can't do them. We'll see in section 7.7 how you can approximate into integrals, okay, but you can't find exact areas, okay, and it's also be a definite integral. Okay, so if we try another one here, what if we integrate e to the x times the arc cosine of e to the x dx? Okay, there's two ways that I can do this. One is I can start off with a use substitution and then use integration by parts, Or I could just use integration by parts. That makes it more difficult though, okay, because I keep track of more things going on. So if I use a u substitution or a t substitution here, I let t be e to the x. dt is e to the x dx. I've got that. Okay, so I'll be able to knock out that part. And the integral then would be the arc cosine of t dt. Okay. Now, whenever you have an inverse trig function and you want to find the antiderivative, the plan should be integration by parts. Okay, that's how, just in general, that's how you do all those problems. So like, in this problem here, this was from 7.1. If I want to integrate just tangent inverse of x, that's going to involve integration by parts. Okay. Well, I'm integrating just cosine inverse of t, so that's going to involve integration by parts. U is cosine inverse of t, dv is dt. I would not have those switch, because if dv is cosine inverse of t, that's not any different from what I'm doing here in the original problem, right? Because I got to know the antiderivative to get v. So this is my only option here for setting up the parts. V is t, and the derivative of cosine inverse of t, that is negative 1 divided by the square root of 1 minus t squared dt. Okay, I would suggest knowing the derivatives of tangent inverse of t, right here, the derivative of sine inverse of t, that'd be this guy without the negative, and then the derivative of cosine inverse of t, that'd be what we see here. Okay, the reason I say that is because you will see problems that involve the inverse trig functions. Okay, so if we use parts here, we're going to have t times the arc cosine of t plus the integral for t divided by the square root of 1 minus t squared dt. Okay, minus and negative means plus. So the next thing is getting this integral here. You can use just a straight u substitution and let u be 1 minus t squared. du is negative 2t dt. I've got a t dt up top, right? So a negative 1/2 would come out of the new integral there involving u. And I got a minus 1/2 times the integral for u to the negative 1/2 du, which the antiderivative of that would be u to the 1/2 divided by 1/2. The 1/2s cancel. So I have, my answer would be in terms of x here. So t is e to the x, right? So I'm going to have e to the x times the arc cosine of e to the x minus the square root of u. Well, u is 1 minus t squared, but t, again, is e to the x. So I got the square root of 1 minus e to the x squared, the same as e to the 2x, plus a constant. So that'd be the antiderivative there. Okay. Again, there's no set of hard, fast rules here to follow. You're just, but it's good that we're seeing, a bunch of examples, and that's the idea that I'm trying to show you here in these videos, just to give you a bunch of examples to so that you can integrate without somebody holding your hand and saying, oh, this is integration by parts, or this is partial fractions, or whatever. Okay, it's so the idea is for us to figure out which technique to use there. Okay, I'll go ahead and do these. Let's see, I got 3 more examples left, and I got this one, and then these other 2 here. I'll do that in the last video. We'll go ahead and stop the video right here, though.